In this problem, we're analyzing a horizontal Atwood machine. So we're given a cart with a mass of 3.2 kilograms on this level track. The cart is sitting on wheels with negligible friction, and that cart is tied by a string to a hanging mass of 2.5 kilograms. The string is draped over a pulley that we consider light and frictionless. And then the two things we're typically interested in for an Atwood machine, we want to solve for the acceleration of the system, so that's little a, and then the tension in the string, big T. Now, one of the things that's been done for us in the diagram already is that our acceleration vectors are shown in the actual direction that the system is going to move. And it's critically important to treat that acceleration in a consistent way. So what we're going to do is say the positive direction for each of these masses is the actual direction of the acceleration. And what that does is it forces A to represent a positive number in each equation that we write down. If you're inconsistent about your definition of A, like if you analyze it so that one A is positive and the other is negative, you'll have the same letter representing two different quantities in your equations, and it's going to blow up the algebra. You won't be able to solve the problem. So for us, we're calling the actual direction of acceleration the positive direction for the force analysis on each mass. So now it's time to get our forces into the diagram. So we'll look at the 3.2 kilogram mass first. We have the tension in the string pulling to the right on this guy. And then for completeness, I put in the force of gravity pulling down on this mass. And just to be general for the moment, I called that M1G, where M1 is 3.2 kilograms. And then we have a normal force of the track pushing up on that mass. Now, because there are no other vertical forces interfering with this problem, the normal force is just going to be equal to M1G, and those two vertical vectors are just going to cancel out. So we don't actually need them for the analysis of this problem. But when we start looking at Atwood machines with friction, well, friction depends on the normal force. So I included that in this solution just so we're making a habit of putting the normal force into the diagram. Now on our hanging mass, we have the tension pulling up. So remember that strings can only pull, and then provided this is a light string and the pulley is light and frictionless, the tension is going to be the same everywhere in the string. So that's a tension of T pulling up on the 2.5 kilogram mass. And then finally, we have the weight of the 2.5 kilogram mass. And for now, I just called that M2G just to stay general about it. So M2 is 2.5 kilograms. Now we perform the force analysis on each of these masses. And what I mean is we're applying Newton's second law to each one of these guys. When we look at M1, in other words, the 3.2 kilogram mass, our acceleration is purely horizontal and it's caused by that one horizontal force. So when we write down F net equals MA, it's very simple. F net is just T, that's the only horizontal force. And then the size of the mass is M1 and its acceleration is unknown, and we just call that A. And again, A is going to turn out to be a positive number because we lined up our positive direction with the actual direction of the acceleration. Now we do the analysis on M2. And M2 has two relevant forces acting on it. And remember, we're going to call downward positive for this guy, so we're lined up with the direction of acceleration. So M2G, we're going to count that as positive minus T. So we count T as negative. That's pointing upward, which is the negative direction for our analysis. That's equal to the size of the mass, which was M2, times its acceleration, little a. So there's our classic system of equations for an Atwood machine. And I'm going to go ahead and just solve this symbolically before we put any numbers in. So when we add the left-hand sides here, the T's are going to cancel. And this leaves me with M2G is equal to M1 plus M2, just doing a little factoring here, times A. So we solve for A. And A turns out to be M2G over M1 plus M2. So that's our general solution, and then we'll go ahead and plug some numbers in. M2, that was 2.5 kilograms. G, we're going to use the approximation 9.8 meters per second squared. M1, that was 3.2 kilograms. And again, M2 is 2.5 kilograms. And when we run the numbers on this to three significant digits, we end up with 4.30 meters per second squared. Finally, we want our solution for the tension, and that's very easy to get by substituting back into our first equation. On the left-hand side of that, we just have T isolated already. So we have T is equal to M1A. So our general solution, we just take our solution for A, that was M2G over M1 plus M2, and we just multiply it by M1. So we end up with M1 M2G over m1 plus m2. Now we just plug our numbers in, and when we run the numbers on this to 3 significant digits, we get 13.8 newtons. Now I want to mention a couple short notes on checking your work in a problem like this. First, and this is sort of the crudest point, is you should make sure that your acceleration is always less than free fall. So free fall is as fast as anything could possibly fall in a gravitational field. Your acceleration should be slower than that because in this case, we have gravity pulling the 2.5 kilogram mass down, but then it's responsible for dragging even more mass, 3.2 kilograms, sideways. The second point I want to make is that you can sub in that 13.8 newtons for the tension and redo the force analysis on each individual mass and just verify that the acceleration comes out to 4.3 meters per second squared. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.